I was trying to tell you that alkyl halides preparation and chemical reactions. These are the two aspects which we will learn in this topic. First, we'll see preparation of alkyl halides right from alkanes. Okay, if you have alkanes like this, a generic reaction makes that X2, as it reacts, you get alkyl halide plus HX. This usually happens via free radical mechanism. The rate of reaction will be more for F2 as compared to that of X2 and so on. Okay, then when it comes to fluorine, it is highly explosive reaction, and iodine is highly reversible reaction. This is reversible reaction. That's why these two we often do not see much, when it comes to reactivity. So what we will usually do is check out selective, mostly for chlorine and bromine. So reactivity wise, chlorine is more reactive than bromine, while selectivity wise, Br2 is more than Cl2. This is more selective than Cl2. Got it? And in fact, if you compare the selectivity, the rate of, X2 at 1 degree, 2 degree, and 3 degree positions, if you compare, if it comes to chlorine attack at 1 degree, 2 degree, and 3 degree positions, it will be in the ratio of 1 is to 3.8 is to 5. While when it comes to bromine, the attack at 1 degree, 2 degree, and 3 degree will be 1 is to 80 is to 1600. So that clearly shows that bromine is extremely selective towards more stable radical positions. Therefore, if I put an example like this, okay, isobutane, then you will notice that, sorry, isopentane, then you will notice that this is Br2 and H nu reaction. So here we will get bromine at this position, which is major. I mean, 99.9% will be this one only. So that is major. Okay. While if it comes to chlorine, correct. So if you notice for chlorine here, so there is Cl2 and H nu. So you will get multiple products here. So you can get chlorine here also. You can get chlorine here also. Okay. You can get chlorine here also. And you can get chlorine here also. Okay. These are the four structural products what you will get. This comes approximately 39%. This comes around 30%. This comes around 15.20%. Got it? And 1 to 2 percentage. Clear? So you can see, I mean, based on this, at tertiary position, we have only one, right? And when it comes to secondary position, we have two hydrogens. So how do we usually calculate that? So you can check out. Here we have 6 into 1 hydrogens at those position. So we will have total of 9 alpha hydrogens plus 2 3.8s plus 1 5 of it. That is a percentage amount which you will get in the first case. Got it? And second case, if you notice, this is around 1 into 5 upon 9 into 1 plus, see, that is 9 into 1 plus 2 into 3.8 into 1 point, sorry, plus 1 into 5, that into 100. So also into 100. Okay. And here you will see this is around uh, 2 into 3.8 divided by 9 plus 2 into 3.8, correct, plus 1 into 5 into 100, correct. So percentages, I wrote it a little wrong here. So this comes approximately around higher percentage, so around 35 percentage. This comes around 32 percentage correct? This comes around 29 percentage, and rest 1 to 3 percentage maybe here. Okay, so this is how you will get the product formation. So you need to typically calculate and only check which one is major whenever you have these cases. Okay, this is how we get an alkyl halide specifically through alkanes using uh, chlorine and bromine case. Next, we can also make alkyl halide using substitution at allylic position. So allylic substitution can also make this into alkyl halide. For example, if you have a propene group like this, and then you are reacting with NBS in the presence of H nu. NBS is N-bromosuccinamide, which will give you this bromine substitution. Structurally, NBS will be like this. Here we have N with bromine on it. Okay. On heating, it will convert into, basically when you heat this, it will convert into a radical form like this, double bond O, and N dot here, and Br dot will come out. That Br dot will terminate to give Br2, a small composition of Br2. Now remember, when bromine is in a small composition, it usually uh, gives uh, more substitution than addition reaction. So Br will not get added onto this position. Another way to look at it is this: if you react with Br2 at an extremely high temperature, as high as 500 degrees Celsius, in that case, bromine will only go for substitution as major. Addition will not happen. Addition will not happen, but substitution is more favorable. Okay, at high temperature, at high temperature, substitution is more observed than addition. Substitution is more observed than addition. This is about allylic substitution. Correct. In fact, if you even have alkanes, for example, if you have an alkane like this, tert-butyl alkane here, that if you react with NBS, here also it can go substitution, giving Br here like this. Okay. Even if you have like this with only NBS given. So unless NBS, when it is offered, whenever NBS is offered, you always go for more substituted bromine position. Now listen, is the interesting fact here. Note, put it as a note here. The note is, if you have a pi bond, for example, and you are using NBS, but also you have added that NBS in in water, in H2O. NBS is present in H2O. If NBS is present in H2O, at this time it will go for addition only. That means first the bromine addition will happen, and then water will add on to this position. Bond will open up, and then you will get Br and OH. So this is a typical same as, same as Br2 H2O addition. Okay, so just keep that in mind, that if NBS is not given in heat, or if specifically mentioned that it is in aqueous solution, okay, then we will always do simple electrophilic addition. We will not do substitution. Correct. So be careful about allylic cases, everyone. So please note down, uh, go through it once quickly and check if you have any points to be discussed again. Now let's talk about alkenes. So the second reaction is from alkenes. Second. So basically, in case if you have to get alkyl halides from alkenes, from alkenes we have learned, all the mechanisms before this. We learned it as the reactions of alkenes, correct? So wherever you have a C double bond C, and then you react with HX, correct, concentrated. So that includes chlorine, bromine, iodine, and so in that case, we will expect H and X to form following following Markovnikov addition. Markovnikov Markovnikov addition. By following Markovnikov addition, we'll get these products. Got it? This is an electrophilic addition reaction. Got it? Let me take with an example. Suppose if you have an pi bond like this and then you are reacting with HBr, correct? Then mechanism wise, first what you will do, we will make an H plus addition here. So pi bond will go, try to push this H plus addition and favor to make an H addition here, and positive charge will come here following Markovnikov's rule. And this is intermediate 1. And from there, you will again get, you know, carbocation rearrangement. So this will make it 1,2 hydride shift, that makes it intermediate 2. And once you get an intermediate 2, then Br minus will go and make an addition here, and that will give you major product. So this is major product. So this is how the product will come, major product. Clear? So there is a typical formation of carbocation. So the first formation of carbocation is the rate determining step. And since it is an addition reaction, please check, in addition reaction energy should be overall released. Okay. So reaction will go like this, reach to an intermediate. From there it will go to another intermediate, and eventually it go towards product. So reactant, intermediate 1, intermediate 2, and product. Okay. So this is how typically you'll get the product formation. Close the door. Close the door. Sorry. Please check. It is an exothermic reaction because overall it is an addition reaction happening. Okay. So we have done this before. So I hope that everybody is clear about, what's happening here. Right. Notice next one. Even if you have an reaction from, I'll do with alkynes also. First, let me finish alkenes only. So with alkenes, I hope all of you got it, how we get this one. Along with that, this is about hydrohalogenation. The second type of reaction, let me put this as A reaction and B reaction here. So the B reaction is about if you have a double bond and then you're reacting with X2 in the presence of CCl4, then you will notice X and X being formed here. So that is, in case, typically if you notice the mechanism, I'll make a quick mechanism. We have done all of this before. So this is how the bond breaking take place, and a bridged halogenation, a bridge halonium bridge intermediate will be formed. This is halonium bridged intermediate. So this is the type of intermediate you will get. This is the rate determining step. And once you get that, the second X minus will always attack on the more substituted position. So overall making this as an anti-addition. Hence, you will get one X here, the other X addition here. Okay. Which means, guys, suppose if it is stereo specifically given, that is, if the compound is given like this, a trans molecule, ethyl here and phenyl here, like this, and then you are treating this with Cl2 in the presence of CCl4, correct? In that case, you know that this is an anti-addition, this is a trans molecule. So trans and anti will always give you uh, Erythro product. Erythro means chlorine and chlorine on the same side, H and H here, ethyl and phenyl here, like this. Okay, this and its mirror image. So you can see, so you can get this as chlorine, chlorine, H, H, ethyl and phenyl. So this will be the product. So this will be uh, these two will be enantiomeric product with 50-50% each. Make this as a racemic mixture. Okay. If it was ethyl and ethyl instead of phenyl, if you have only ethyl, then it is only one product which is meso. Okay, so that will be the product here. So I'm sure you guys can remember that. The same type of question, if at all I ask you in interhalogenation form, like this is a cis form, and then I'm adding I and Cl here, let's say ICl in the presence of CCl4, then first you need to check out which one is more delta positive and delta negative. So this iodine is more delta positive, so that will make a halonium bridge, and then Cl minus will attack on it. So hence we will get a product like this where chlorine is coming out of the plane, iodine is inside the plane, or vice versa. Chlorine is inside the plane and iodine is coming outside the plane, like this. So these two are the products. Again, this is racemic mixture. This is racemic mixture. Done. Finished, everybody. Please notice the reactions quickly. This is about halogenation form. Third is from alkynes. From alkynes, what kind of a reaction will happen here? See. So if you have R, C, triple bond, CH, and if you are making an HBr addition, the first addition will be such that we will have, uh, Markovnikov rule should be followed, which makes it CH2, and then we will get Br here. This is first equivalent, correct? If I add one more equivalent to that, that is HBr with one more equivalent. So this will typically go for electrophilic addition, and one more Br will come in the same position. So this is the major product form. So when it comes to alkynes, you will get geminal dihalides. You will get this as geminal dihalides. Okay. Next thing. Fourth, you can see from alcohols. In fact, alkyl halides mainly are prepared from alcohols, everybody. Got it? So alcohols will make a lot of range of reactions when it comes to alkyl halides. The first thing you need to understand is, we'll individually check out, first with concentrated HCl. Then what will happen? See, in concentrated HCl, in case if you have 1 degree, suppose if you have 1 degree alcohol and then you are writing this with HCl concentrated, correct? You will hardly see any reaction happening, no reaction. Mm, Most importantly, you should understand that when I'm using HCl, which means there is no water content here. Even if it is there, it is in a very small quantity. In such case, breaking this HCl becomes a challenge. So reactivity will not be very high. I mean, in fact, there will be hardly any reactivity where HCl is breaking and Cl minus is becoming a nucleophile to attack. So this reaction usually does not take place. Okay. Hmm. Next, it is in a 1 degree alcohol. In 2 degree alcohol here, if you have it like this, 2 degree alcohol plus HCl with concentrated HCl concentrated, then you will get then you will get Cl here plus H2O, but in a very poor yield, very poor yield. You will not get good yield of it. Okay. Which means 1 degree, 2 degrees would be hardly operating on HCl. Only 3 degree will operate. 3 degree alcohol, okay. If you react with HCl concentrated, got it. Then you will get Cl here plus H2O, typically following SN1 mechanism. Typically following SN1 mechanism. So which means if there is any rearrangement also, it would happen. Okay, correct. So it is to do with, stability. First, carbocation stability is not so much here. This is very, this is to be smaller extent of stability. Here you will have large extent of stability. So whichever has a stable carbocation formation, they can give this reaction, not just for 3 degree. Okay, which means, let's say if you have like this alcohol here, and then you have HCl concentrated. Now in this case, the reaction will take place. Reason is very simple. This is a very stable carbocation. Okay, here CPM cyclopropyl methyl carbocation is very stable. Cation is very stable. That's the reason why this will happen. Okay. So I guess this part is clear. What will happen with concentrated HCl? Okay. Second, with concentrated HBr and concentrated HI, we can simply write it as concentrated HX. In this case, reactions will take place. So you can go it this way. If it is at a 1 degree position here, and then you are using HX concentrated, correct. In that case, you will have X here plus H2O, but reaction is driven via SN2 mechanism. So here bond will typically break, but often go for SN2 mechanism. If it is a 2 degree alcohol, then you treat with HCl, HBr or HI, then it will give you X here, okay, via SN1 mechanism. This is via SN1 mechanism. Similarly, if you have a 3 degree alcohol plus HX concentrated, then you will get this as X plus H2O. This is via SN1 mechanism again. Now notice rate of reactions here. Rate of reactions for this will be greater in the case of HI, HI much greater than HBr, greater than HCl. Okay. And type of alcohols, if you compare alcohols, then the rate will be ROH 1 degree greater than ROH 2 degree alcohol and ROH 3 degree alcohol. Sorry, I wrote it ulta. 3 degree alcohol should be more than 2 degree and 1 degree. Because here we often notice the stability of carbocation. So more stable carbocation, the reaction will happen faster. Okay. So please have a note. Please check what happens with alcohols when you react with HX. So one thing we realize is that getting a chlorine is a bigger challenge here, isn't it? Chlorine on a 1 degree or a chlorine on a 2 degree is very, very challenging. So this is where we can make an improvement of that. And, let's see how we can do that. This is using something called Lucas reagent. Lucas reagent. Okay. So this is very important for us. So Lucas reagent is when you have HX concentrated, and adding that with ZnCl2 anhydrous. Okay, Hn concentrated adding with ZnCl2. Now this will ZnCl2 anhydrous will help to make that 1 degree reaction or 2 degree reaction, but again not to a larger extent. But at least we will be it will be useful to actually detect the type of alcohols. That is, if you take 1 degree alcohol, let's say RCH2OH, and then react with ZnCl2 first, correct? The first reaction is the lone pair trying to attack on zinc here. That will cause RCH2OH plus and ZnCl2 minus. This is like step one. And then once you get here, you can notice this compounds this compound will be able to react with HCl here, correct, and try to release up this zinc here. So basically we will have plus here, isn't it? And then we can have this as ZnCl2. Sorry, my mistake. Sorry, my mistake. Check this out. So here this can convert into RCH2, this H here, OH here, and ZnCl plus Cl minus. So this will become a source for releasing Cl minus. And once you get this Cl minus here, now few moles of this CH2OH here, correct, where you have already been connected with ZnCl2 minus, and this Cl minus can connect here to remove this bond, correct, and that will convert into ZnOH and Cl2 here, correct, with a minus charge still carried, plus RCH2Cl. This goes via SN2 mechanism, because here stable carbocation formation is hardly observed. Okay, and this compound will eventually become ZnCl2 again, and OH H plus will take that H2O and convert into H plus and convert into H2O. So this is how you will get the product again, and you will get a 1 degree alkyl halide. Okay, but when it comes to 2 degree alcohol here, okay, but this is a very slow process, and it will take 30 minutes and above. 30 minutes and above. And in most cases, in JEE mains specifically, they will be giving you the heat as well to ensure that there is reaction happening. That is HCl with ZnCl2 anhydrous. If this is given, heat is also been mentioned just to get this X. Now, problem is this alkyl halide which is present in a large quantity of alcohol will appear to be white turbidity. So it will be a white turbid formation. Got it? So it will form a white turbid here. So next, notice the second point here. Second reaction is if you have R, CH, R and OH. If you have 2 degree alcohol, 2 degree alcohol, and then you are reacting this with Zn Cl2 anhydrous. So the lone pair will attack here, and this will become RCHR connected with OH plus and ZnCl2 with minus charge here, and this this easily breaks into carbocation, because from second degree onwards, it will start showing a stable carbocation form. So you'll get this Zn Cl2 OH minus. And here Cl will release more easily, getting this into Zn OH and Cl. So it is that Cl minus which is released will be able to attack RCH plus here. So Cl minus will attack on it, and you will be able to get this as RCH, Cl and R. This is the product. Clear? So for 2 degree and 3 degree, you will see the same product. This will be a white turbidity. This will be white turbid. And you know what? This will happen between 2 to 10 minutes. This reaction will finish in 2 to 10 minutes. But if it is tertiary, tertiary will happen instantly. So suppose if you have an alcohol like this, and then you are using HCl in the presence of ZnCl2, it will give an instant turbid here. So this will also be white turbidity, correct? And this will be instantaneously. Why it is instantly? Because stable carbocation formation. So wherever there is a stable carbocation formation, this reaction would happen quite fast, and this is a method to differentiate 1 degree alcohol, 2 degree alcohol and 3 degree alcohol using Lucas reagent. So please go through it once quickly, everybody. Now question is, right, now the question is about figuring out in which case you will have more of white turbid, but it will take shorter time instantly or long time. See, find find the time taken for white turbid formation. White turbid formation. One second. Notice this. Find the time taken for the white turbid formation in this for the following cases. For the following cases. Okay. So what are all those? Please check. First one, you have OH here. You have OH here. You have OH here. Second, you have OH here like this, and we have OH on the phenolic position. We have OH on benzoic position. Okay, then we have tert butyl alcohol, and we have an alcohol like this. And if we have a bridge position like this with OH here, cyclopropyl alcohol, cyclopropynyl alcohol, CPM, cyclopropyl methyl alcohol. Okay, and in case if you have tropylium alcohol, correct, correct. So check out all these cases now. You can pull this down. Yeah. So for all these cases, if you notice the time taken, let me write down. You also do it with me. First, in the first case, you will see this is between 2 to 10 minutes because it is 2 degree. This is greater than 30 minutes because it is 1 degree. This is instantly, so instantaneously. This is also instantaneously because stable carbocation, very stable carbocation. This is no reaction because phenol is present. You cannot dehydrate this because of the double bond character developed due to resonance. Here, this will be instantaneous because a stable benzyl carbocation. This is also instantaneously stable 3-degree carbocation. This will take greater than 30 minutes. This will be no reaction again. At this position, formation of carbocation is not observed. Then, if you have it at this position, also no reaction. Formation of carbocation at cyclopropyl position is impossible. Here, carbocation will form because the ring will become aromatic. So this will be instantaneously. Because the minute you get a positive charge here, the ring will become aromatic. This will also be instantaneous because it is CPM carbocation. This is also instantaneous because it is tropylium carbocation. So yes, these are the formation which you will notice. So this is the time taken for all these cases. Clear? Done. So this is something which you will be asked from Lucas reagent. Okay. And most importantly, which type of reactions will happen from which alkyl halides, whether it is chlorine, bromine, iodine, which will happen. Now, next notice. The next type of reaction we will see here, second type of reaction we will see here is action of PCl5, PCl3 and SOCl2. Action of these three. How does that happen? So check out reaction wise. First, RCH2OH plus PCl5. This will make a reaction to form RCl plus POCl3 plus HCl. Okay. Typically, it goes for SN2 type of reaction if it is 1 degree, and SN1 reaction if it is 2 degree and 3 degree. Okay. If it is 2 degree alcohol and 3 degree alcohol, it will usually go for SN1. If it is 1 degree, it will usually go for SN2 reaction. Okay. This is normally this reaction is normally made in ethers. Yeah. How does the reaction happen here? Check it out. So, first, if you have PCl5 solid, remember PCl5 exists in a solid crystal form, and this exists as PCl4 plus and PCl6 minus. This is how it exists. So, once you have this PCl5 here, now the reaction will take place where CH3OH reacts with the electrophilic position of PCl5 and it will attack directly to make it CH2 with OH plus connected with phosphorus and 4 chlorines on it. And this is what is the intermediate you will get. And what you would notice here is that PCl6 on the other hand, PCl6 in ether will start releasing this into PCl5 plus Cl minus. This is what happens in ethers. Okay. So there is an available Cl minus in the solution. Got it. So therefore, this Cl minus which is available, it will take H plus here. Okay. and convert this into RCH2O PCl4 plus HCl. So this HCl will come out as vapors. Now this is the next intermediate which is forming. Now notice this intermediate here properly. Correct. Here, if you have four chlorines, correct. So Cl, 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 and Cl. The lone pair present on it will push here to remove this chloride. That will convert into RCH2O double bond P with a positive charge and have three chlorides on it with Cl minus. Okay. And that is exactly what will trigger the next reaction here. So that is this Cl minus will go attack here and bond breaking will take place at this position. So what do I get? I will get this as RCH2Cl plus POCl3. Correct? These are the products we are expecting. This is the main product. Then we'll get POCl3 and then we'll get HCl. Okay. This is how the reaction usually takes place. Got it? Now you can see at 1 degree position when it is there, it will typically go for SN2. Now the reason is why is this happening? Pretty simple. The reaction why it is initiating where oxygen is trying to push it electrons towards bond towards phosphorus is bond dissociation energy of P double bond O that is greater than bond dissociation energy of C single bond O. So oxygen would like to associate more with the phosphorus as compared to that of carbon. That's why it is trying to donate its electrons, trying to convert into a double bond character, and then it will break. Clear? Please go through the mechanism quickly. Everybody, I'll give you a minute's time. Right. So the next reaction is about taking alcohol, reacting with PCl3 again in ether to convert this into, you have to take 3 moles of it. So you can get 3 moles of CH2Cl plus H3PO3. This will make it H3PO3 formation. Okay. So how does the mechanism operate here? So you got RCH2OH plus PCl3 here. Got it? So we will get this as RCH2OH and PCl3 plus and minus present. Okay, plus and minus present. Got it? And this will become a feeder for the second molecule. So imagine like this, if you have 2 moles, I'll directly write with 2 moles here. So for 2 moles, if these 2 moles have been formed here, correct? So in this case, 1 mole here, right? So we take it, yeah, copy that here. If you take it with 1 mole here, so we will have here this as Cl, Cl, Cl with minus charge. And the second mole RCH2OH plus and PCl, Cl and Cl minus charge. So from here this Cl will go and attack onto this position and break this bond. Okay. So that will leave behind RCH2OH plus and PCl and Cl. Correct? And the same thing will happen with the next mole also. So if you have it this way, now for this compound, similar type of reactant here which is forming, that will again attack back here on this position, correct? Removing this OH here, correct? So again, the other product which I have to write down is R CH2Cl. So here also you'll get the same thing. You'll get this as R CH2Cl plus POH Cl and Cl. This is what you will get. Now once you get this POH Cl and Cl, now this will be reacted with the third mole now. That is RCH2OH. This will attack here and you will start getting RCH2OH plus and POH Cl and Cl with minus. So could you imagine the next molecule will again react on this position here. Okay, so where was the original molecule? This one. This will again make a reaction on this position here like this, and that will relieve this part. So now we will have RCH2OH PCl2. The other compound what you have is RCH2Cl plus POH twice and two Cl groups with minus charge. Okay, correct. So this minus again from here Cl will go away. You will get PCl and OH twice. So can you imagine? This will keep on happening stepwise till it completely becomes POH thrice. So what has typically noticed is that there is not a uh, complete transfer of Cl minus with H plus. So HCl formation is not observed at all. So everything will convert into H3PO3. Correct? So it's like chain reaction. It's like chain reaction till all of PCl3 converts to POH thrice. Now POH thrice, mind you students, we have OH, OH and OH here. So this lone pair will attach here. So minus will take here. This is tautomerization. So it will undergo tautomerization to get OH, OH and P double bond O and H. Sorry, like this. So this is phosphorus acid. This is phosphorus acid. So it will form phosphorus acid. All okay? Please check. Don't worry about the mechanism here. Mechanism is little complex. It will never be asked. Okay. But just to give you an idea that there is no formation of HCl, I shown you how this, movement of chlorine will happen. The next reaction is about RCH2OH reacting with SOCl, SOCl2. SOCl2. SOCl2 is called as thionyl chloride. So that will be thionyl chloride. And thionyl chloride, when you react in the presence of ether here, it will start becoming RCH2Cl plus SO2 plus HCl. Here you will see HCl vapors will be coming here. That is a product formation. Okay. Now notice the mechanism here. So in this case, mechanism goes like this, where RCH2OH will attack S double bond O, Cl and Cl. So first the lone pair will attack here. As soon as it comes over, we'll get this as RCH2OH, and sulfur will get this as O minus Cl, Cl this way. And this O minus, as it comes back, now it can release the Cl minus. And that Cl minus will take H plus and push the electrons here. So that's how you will get this as RCH2O and S double bond OCl plus HCl vapors will be out. So in this reaction, you can see HCl vapors will come out easily. because there is a push from the minus charge of the oxygen. Now, this is a very interesting intermediate here. If I write this intermediate properly, you can see we have CH2, we have oxygen, then we have S double bond O, and then we have Cl here, correct? Now, this basically starts showing a carbocation behavior here as this bond will start moving. And you will still have the affinity towards oxygen's lone pair with sulfur and double bond O. But at the same time, sulfur will start losing out bond with chloride and start gaining negative charge. Okay, this is how it will happen. This is called intimate intimate ion pair formation. So there will be an intimate ion pair formation. So imagine as if you have this bond and then you can rotate it around, correct? As you rotate it around, now you will notice that this orbital and this orbital will come almost close to each other and they'll start bonding, and you'll start getting this Cl minus attacking here, getting this as CH2 Cl plus SO2, CH2 Cl and SO2. Okay. Now, what is the important part? If you go back to these reactions, they are all SN2 driven. Here also it is SN2 driven. Here also it is SN2 driven. Correct? Everywhere there is SN2 reaction. So this is also an SN2 type of reaction. Going back here also it is more of SN2 driven. While if you compare here, this is not exactly SN2. SN2 means it should always attack from the back side. But here where the bond is breaking, it is attacking from the same side. So hence this is this is an this is an SNI mechanism. This is called SNI mechanism. SNI means internal attack. Okay. Internal attack of nucleophile. Okay. So that is the internal attack of nucleophile, and we call it as SNI attack. Please go through it once quickly, everybody. Right. I guess you're done. Now notice the same reaction. Let me write down that here. This is SNI. Okay. But the same reaction, if at all you're performing instead of ether, you're performing this in pyridine. If you are using this in pyridine, then the reaction will go via SN2 mechanism. And this reaction name is called Darzon's reaction. Darzon's reaction. Okay. So how does that operate here? Please check. So first same thing here, RCH2OH, RCH2OH. Till this step everything is same. S double bond O, Cl. Up to this step there is no problem. But since pyridine is a strong base also, it can attack internally. Push it here to change this part into this form. So we have RCH2O with sulfur O minus with the pyridine form here like this, and Cl getting a positive charge here. And in that case, now this will close here to remove the chlorine completely. Now the chlorine will be completely relieved out, and I'll get this as RCH2O S double bond O with pyridinium salt here with plus charge. This is connected like this, okay? And now we have Cl minus available. So you can see now we have Cl minus available to attack. So this time Cl minus will go, right, sorry, the lone pair from here will be pushed into this form. Cl minus will attack and this bond will go. So that's how you will get this as R CH2Cl plus SO2, and this pyridine which is forming can react with the HCl initially released and convert this into pyridinium chloride, like this, with H plus and Cl minus. So now notice this attack. This attack is now SN2 type of attack. This way. So this is like an SN2 type of attack. Hence the reaction will go via SN2 mechanism. Please check. How that's clear? Please just quickly. So check how the questions can be asked. Examples. A. In case if you have OH, deuterium, hydrogen, and methyl here, then you have PCl5 reaction in ether. Then you will write an SN2 product, so which is Cl here, methyl here, deuterium, and H via inversion. This is the product formation. And in case if you are writing uh, for same reaction for SOCl2, only SOCl2, only SOCl2, then you'll write it as SNI mechanism, and this time you will make a retention product. So this is called retention product because the configuration is retention, and here it is an inversion product. Okay, so one is retention, the other one is inversion. Now, important point to note here is out of following PCl5, PCl3, and SOCl2. SOCl2 makes best reaction to yield alkyl halides as SO2 and HCl vapors. Okay, SO2 and HCl vapors release as products. So you will not have anything else but a clean alkyl halide formation. That's the reason why SOCl2 is more preferable. Clear? So this is a preparation from uh, alcohols, everybody. So from alcohols, this is how you make the alkyl halides. Next, let's see preparation from fourth one. This is preparation from alkyl halides themselves. So alkyl halides to alkyl halides, how do we prepare? So check first one. In case if you have RCH2X, where X is chlorine and bromine, then we are treating this with NaI in the presence of acetone. The presence of acetone. In that case, you will get this as RCH2 iodine plus NaX. NaX. NaX forms precipitate in acetone. Okay, precipitate in acetone. And it is this precipitate formation, okay, which actually helps. It is the precipitate formation which actually helps in making this product, I mean, making this reaction happen. Otherwise, iodine is more easily withdrawing group, correct? So this will go backward reaction. It should have been more in backward reaction, but why it goes in the forward direction is because NaX can form a precipitate here. Okay, this is completely SN2 driven reaction. So if you are expecting any reaction like this with halogen here, like this with I minus in the presence of acetone, then you will not find much reaction happening, correct? So while if you have X and I minus in acetone, at secondary position, it can still offer to give SN2 and you will see the product formation. Primary position, anyway, this reaction will give you the product. So it is, this reaction is, this reaction is highly SN2 driven, SN2 driven and known as Finkelstein reaction. Finkelstein reaction. I suppose this reaction type is clear, everybody. Then see the next reaction here. The next reaction, if you notice here, this is a very similar reaction again. Okay. Again, if you react with Rx, where X could be chlorine, bromine, or iodine, and this, if you react with AgF, AgF, then in the presence of ether, correct, or any other solvent, or even in aqueous solution also, ether or aqueous solution, correct. But typically in aqueous solution, alcohol formation is more observed, so we'll try to avoid more aqueous form. In that case, you will get this as Rf plus AgX formation. AgX will also form a precipitate. Okay. If it is AgCl, it is a white PPT. AgBr, it is a pale yellow PPT. Pale yellow. If it is AgI, it is dark yellow PPT. Okay. So this is a reaction that happens. So this type of reaction is also SN2 driven. SN2 driven. Okay. Also SN2 driven and known as okay, Swartz reaction. Swartz reaction. So one is Finkelstein, the other one is Swartz. Got it? Now, other reagents which will do the same job, okay, other reagents for fluorination. Other reagents for fluorination includes COF2, got it? COF2, HgF2, got it? Then we have SF4, got it? SBF3. These are all in DMSO. So if you take it in DMSO, we will have similar type of reaction where we can get some precipitate of halogens and fluorine will get substituted on it. Okay, I suppose all of you understood that. Please go through it once quickly. What are Finkelstein and Swart reactions? Both of them are SN2 driven. Right. Both reactions are called halogen exchange reactions. These are halogen exchange reactions. Well, one thing you need to keep in mind is that by chance, if there are two halogens on vicinal position, and then you are reacting with NaI acetone. So imagine like Finkelstein reaction happening on both the positions, you will get two iodides. And you need to learn that uh, vicinal iodides are unstable. They will easily convert into I2 and alkene. So you will report this as the major product. So you will not report alkyl halide, but you will report alkene as a major product. Done. So this is the halogen exchange reaction, everybody. While if you have vicinal dihalides, then instead of getting into uh, simple alkyl halide, it will go towards formation of alkene. Okay. So I hope this reaction is clear, everyone. Next. Fifth one, what we will see is from aldehydes and ketones. Aldehydes and ketones. See, from aldehydes and ketones, reactions are simple here. So if you have any aldehyde or a ketone, let's say I'll take ketone as a reference, and if at all I treat this with, DMSO, DMSO, DMSO is S double bond O, Cl and Cl. Then you would notice that both this Cl will get exchanged for that one oxygen converting into SO2. Got it? So you will get this as geminal dihalides. So the product what you are getting is geminal dihalides in this case. Mechanism is not so important here, but I'll just give you a glimpse of it. How does it happen? Check R, C, double bond O, R dash. It will try to attack on this sulfur here, okay, and then pushing down the chlorine away. So we will have this as R, C, R dash, double bond O with S, double bond O, Cl plus and Cl minus released. So this Cl minus will be released, getting into oxygen connected group here. R dash, one chlorine will come at this position, and think about doing it same one more time. So this will push here, Cl minus will come out here. So that will make the product as R, C, R dash with Cl and O, double bond S, double bond O plus charge, and Cl minus release. So release Cl minus will attack, remove this oxygen, and thus we will get minus SO2, and product will be R, C, Cl, Cl and R dash. That's how you will get geminal dihalides. Geminal as in both the halogens on the same carbon, vicinal as in halogens on the adjacent carbons. Okay, this is from aldehydes and ketones, everybody. Very simple thing. We don't have to make it anything difficult here. So two halogens will get attached. Sixth is from carboxylic acid. From carboxylic acids. From carboxylic acid, how do we get alkyl halide? Let's see that. Suppose if you have RCH3 Okay, so RCOOH, and you treat something like AgNO3, it will start forming a silver salt here, like this, a silver salt of carboxylic acid, okay, plus HNO3. Now, our role is more to do with the silver salt here. So, when silver salt of carboxylic acid are C double bond O minus and Ag plus. Now, that has been treated with, this has been treated with Br2, it will start becoming Rc double bond O, Br here, and AgBr will start precipitating. Okay. Now, on further heating or exposing to light here, either on heating or exposing to light here, this will undergo a radical bond breakage here. So that means homolytic cleavage will happen. And once you get this carboxylate radical here, Rc double bond O dot, this will slowly convert into R dot and CO2. Okay. So R dot and CO2, this is the rate determining step. This will happen slowly. And finally, when you have R dot plus Br2, R dot and Br2, that will convert into RBr plus Br dot again. So what happened? We'll get this as alkyl bromide. All right. The reaction would happen in a very similar way for halogens. I mean, chlorine and bromine also. Correct. So what are the points to be noted here is this is a step down reaction. This is a step down reaction. Okay. Step down reaction. Step down reaction as in you will notice only, I mean, you'll notice one carbon dioxide is less. Second thing, okay, product yield, product yield will be better in the case of CH3Br then compared to that of C2H4Br, then isopropyl, then tertibutyl. Okay, this will be poor yield. Why the yield is like this? Simple. The radicals smaller it is, better the reaction they can make. Okay. In case if they are bulkier, they will try to make a disproportionation reactions. They will involve more into disproportionation reactions. And this is what you will notice. I'll put this as an example now. Check this out. Suppose in case if at all I have CH3 C double bond OAG and react with I2 in the presence of H nu, correct? If only I have 1 is to 1 ratio, then the product is very simple, CH3I, AgI formation and carbon dioxide. Okay, correct. But if you have same reaction here, but if the composition is slightly more also, if it is 2 is to 1, then this is not the product. I mean, this will be the minor product here, right down here. So this will become the minor product. The major product will be ester itself. The major product will be this one, CH3, C double bond O, OCH3. So this will be major product. Why is that? Because CH3 dot forming, reaction with this ones to form CH3I plus I minus is highly reversible. This will be highly reversible. So that means you will hardly get to form into this. So what will it do? So this same CH3 dot will again terminate with the CH3 C double bond O dot which was forming as an intermediate earlier. And hence you will get this CH3 as major. So remember, especially in iodine, in case if you have 2 is to 1, definitely it will start forming an ester as a major product. All right. Everybody, have you guys understood? So please check the reaction quickly. Okay. This reaction is known as Hans-Stecker-Borodin reaction. Hans-Stecker-Borodin reaction. Okay. So this is one way of getting alkyl halide from carboxylic acid, everybody. I hope this is all clear. Right. The last, by the way, these are all the preparation reactions now. Now let's see what are all the physical characteristics. Physical characteristics of alkyl halide. Okay. Right. So when it comes to physical characteristics, you will see that boiling point of Rx, sorry, boiling point as well as melting point. Melting point and boiling point of Rx will be Ri greater than Rbr greater than RCl greater than Rf. Okay, this is how it will be. Got it? And next, just for the sake of information, if you compare CH3Cl and next, if you compare boiling point or melting point for type of halogens, you will see CH3Cl, CH2Cl2, CHCl3, and CCl4. In that case, number of halogens has increases, the boiling point and melting point dominates. And here dominance is all to do with the molecular weight. More the molecular weight, more is the reaction. So 40 degrees here, 61 degrees here, 71 degrees Celsius, 77 degrees Celsius. So this is the order of boiling point. Okay. Second, dipole moment. Dipole moment. So if you notice, mu dipole moment Ri, right? Uh, sorry, RCl, that too especially CH3Cl will be greater than CH3F. This is an exception here, although fluorine has more polarity than CH3Br here and CH3I here. This is the first dipole moment. Second is number of chlorines. So CH3Cl will have more, then CH2Cl2, then CHCl3 and CCl4. But at the same time, if you're treating this with, in case of fluorides, then it will have CH2F2 has more dipole, then CH2F, then CH3F, and CF4. So these two are exceptions here. First, one exception here. Second, another exception here. So these two are the exceptions here when it comes to dipole moment. Okay. Next, if it comes to uh, uh, is that yeah, second dipole moment. Yeah, solubility. Next one is solubility here. Okay, almost all alkyl halides are insoluble insoluble in aqueous solution. They're all insoluble in aqueous solution. Lastly, density. So when it comes to density, Iodides usually are more denser than chloride and bromide, chloride and RF. Okay, so these are some important physical characteristics we should know. Clear, students? By the way, everything is given in NCRT. I just took directly from NCRT here. So if you could read NCRT once, you will have a better clarity also that how the graphs of boiling point, melting point graphs are given. So you'll be able to figure it out. Okay.